then let's start. I'm happy that not everybody, or that some of you at least, came back, not have given up on that. Adrian told me today that I'm getting all giddy and jumping around when I start talking about templates, which is kind of, I'm not sure if that's a healthy state or not. But apparently you're interested in that stuff, at least marginally as well, so otherwise you wouldn't be here. If you remember last time, 2 weeks ago, we left off where I started to introduce template types. So that is a mechanism in C++ which allows you to define a type which depends on one or more template arguments. And as an example, we implemented that coordinate type which has one template argument t, and the two coordinates stored in that structure are of that type we use to instantiate it. I want to continue today to start. Well, this use of template types I showed you is what templates have been designed for. So create some struct, some type, and make it dependent on one or more template types so you can use it in various contexts like standard vector or list, or all these containers are parameterizable using their template types. But soon after this language feature has been standardized in '98, some guy came up with the idea to do something for which those templates have not been designed for. They discovered that templates are Turing complete. The template system is Turing complete. And if you know what Turing completeness means, everybody knows what Turing completeness means? Do you know that? Well, Turing completeness means that you have the minimal set of operations available which allow you to do all computations, all possible computations, broadly speaking. And that means if templates are Turing complete, that means that you can do computations at compile time, and you can force the compiler to do certain computations for you at compile time. Which was kind of surprising for people, because what that guy, and if you look around you will find that on the internet, came to the standards meeting and showed a program which was printing it was printing prime numbers at compile time in the generated error messages. So that code was... Huh?
Who was it, Alexandrescu?
No, it wasn't. Alexandrescu wasn't born at that point, I believe. No, I don't remember. Just look it up. So that program didn't compile properly, but what it did when it was failing to compile, it was generating error messages which had prime numbers in them. So he showed, yeah, you can use templates to do computations at runtime, at compile time. And it had to be at compile time. Well, it didn't even compile, it didn't even run, right? So it generated error messages. And that was a starting point of the of a heavy abuse of the facility of templates in the language, which is going on until today. And people are, went completely off with that, because it turned out to be a very, very powerful feature, which allows you to do compile time computations, which allow you to do code generation. And I will show you a couple of examples. And some of the examples we already have seen with that advanced algorithm we talked in the first seminar. But we will have plenty of those examples over and over again. What I want to start with is to show how you can use templates to do numeric computations at compile time. And while that is something you might not want to do nowadays anymore, because nowadays the language has additional language features which allow to do that in a much easier and better way, I still want to touch on it because it still has some significance. So last time I was told not to delete anything in my source code here, and just to comment out everything so people could follow what I was doing more easily. So I will just comment out things. What I want to do today or in the beginning is to compute factorial at compile time. Factorial is just multiply all numbers, all whole numbers or all natural numbers from 1 to a given number, and the result of that multiplication is a factorial. How do you do that at compile time? For that, obviously, we want to use templates, because that's the only mechanism we know how to do these computations. So let's create a template which we call factorial. And one thing you already see is that this time I'm using an integer as a template argument. I'm not using a type name, a type as a template argument, but I'm using a integral template argument. And C++ allows you to use integers or any integral types as template arguments, like booleans, integers, longs, and this kind of thing. And for each n you use or you instantiate factorial for, you get a separate type. So in the end, factorial, if I create a variable of type factorial 1 f1 factorial 2 f2, I create two separate types. So factorial 1 is distinct from factorial 2 as int is distinct from double. It's completely independent types which have nothing in common. So we can use integers in order to, or we can encode integers into types. We can represent, or we can generate types which represent numbers. And that is a basis for calculating, doing numeric computations at compile time. Because, hell, the compiler can't do input-output, the compiler can't assign variables. All you can do, you can generate a new type whenever you need a new value. So it's a very functional way of doing things. So if somebody of you has done some Haskell work or other functional languages, you know what I mean, because whenever you create a new result, you don't assign it to an existing variable, you just create a new variable which is initialized to that value, and you can't change that value of that variable afterwards. And that's exactly how computation with templates look like. Whenever you need a new variable, you create a new type which represents the value of that variable. And so computing factorial is essentially creating a sequence of types, each of them representing one of the factorials when you calculate down, right? Factorial recursively, you compute by n multiplied by factorial of n minus 1. That's a recursive formula, right, to compute factorial. So in each time you do one of those multiplications, you create a new type. And each of the factorials you compute is a new type. And that's why I did it that way, because we will create a sequence of types factorial n from n downwards to 1. Okay. What we haven't done, we have created a so-called, well, it's a template, but in our context we can think of it as a meta function. It's a function which is computed at compile time, which is executed at compile time. That's why meta function. That's why people talk about template meta programming, because it's programming at compile time. Let's think about that as a function. And the function takes one argument, which is n, but we haven't represented the result of that function yet. How do we represent the result of a computation in that context? And here people have come up with some pure convention. And we will see that convention applied over and over again when we do metaprogramming, namely that numerical results in template metaprogramming are represented by a embedded static variable. Static int const value. And that embedded variable is always called value. Always. So whenever you see a template which has a static something which is called value, you can just assume that this is a meta function which is used somewhere to do some numeric computations. And the value for now we have to compute our factorial. Well, it's fairly easy, right? What we have to do, we compute n times factorial n minus 1 value, right? So the factorial n is computed by multiplying n with whatever factorial n minus 1 is. And we refer to the result of that computation by doing colon colon value. Well, colon colon means look into, right? So look whatever is defined inside that type. And inside n minus 1 we have another value which recursively unravels that factorial until we get, well, until when? What happens if I execute that? Want to try that? Well, let's try it. So let's see, we want to calculate factorial 10. What will happen if I do that?
It doesn't exit at 0?
It doesn't exit at 0, right? So, well, let's do this. Let's do a std cout factorial value. Okay, so let's compute the factorial of 10. If I compile that, okay, I know what's up. Sorry, I was just wondering why it compiled, but I have the wrong file in my solution here. Give me 1 second. This one. Okay, and now if I compile it, it compiles and compiles and compiles and compiles, and then poof, something happens. Well, the compiler bails out saying recursive type or function dependency context too complex. And what happened, as you can see, we failed to stop at 0. Right? The recursion went on and on and on, and we went into the negative numbers. And at some point, the compiler just gave up and said, no, I can't do that. Obviously, I wouldn't be able to do that either. So what we need is, we need to tell the compiler, or we need to find a way to break that recursion. And in order to break that recursion, we use a technique which is called template specialization. And we will use that technique over and over again as well. And let me write that up quickly, and then I can explain that to you. Static int const value. So what I did, in addition to the main template, I provided a specialization of that template, which is used whenever n is equal to 1. So whenever I use factorial 1, the compiler will not use the main template, but will use this one. And that gives us a breakpoint, because it will go down until it gets to n equals to 1. And at the point of n equals 1, we know the result, which is equal 1. And then it will unravel it back and will give us the computed value. And it's called specialization because I'm providing a special value for one or more of the template arguments, which gives me a special template which is used for that particular set of template arguments only. And for all other values, it uses that main template. You can provide as many template specializations for a main template as you want. And the compiler will do pattern matching and will try to find the one which matches the given arguments best. So it's a very, very flexible and very powerful means of selecting which of the template implementations to use actually. Okay? And if we compile it now, it will compile, and let's see what it does. And it says it's 36,280,000 something. So it's a very small number there. Now you might say, okay, it calculated the factorial 10 properly. I hope it did properly. So if somebody wants to check that, whether the number calculated is the right one. But did it do that really at compile time? Or is that some magic which suddenly moved into runtime and we did runtime computations after all? Well, let me show you the generated assembly code for that. So you believe me, hopefully. For that, I will generate a assembly listing together with a generated code, with source code. And I'm compiling this. And let me open that assembly listing for you. It's here. So this is the stuff the compiler generates internally, and don't get kind of, it looks scary, but the important part is this. Where's my code? Hold on. This is the important part. As you can see, the compiler generated assembly code which contains the result. So the computation of the factorial happened at compile time, right? Because this is code which will then be translated into object code and will be run at runtime. And there's no computation going on at runtime anymore. It just prints the number which the compiler already calculated at compile time. Well, let's do it so that you see that it really changes. Let me just do a 14-year. Integral constant overflow, see? So it's too large to be represented by an integer. So let's do a 9. And if you look at the assembly now, you see that it's a smaller number, right? We had 2 zeros before. So it didn't multiply with 10. The morale, you can do numeric computations at runtime. Well, there are some limitations to that because, as I said, you can use only integral types as template arguments, as bool, integer, long, these things. You can't do floating point computations. Anybody knows why you don't want to use floating point computations with template arguments?
Because if the compilation might give you different results.
Well, you two guys should know it. We talked about that. Why? What is a floating point number? Floating point number is not a
Standard? No, it's not complete.
It's not a complete type. That means not all bit patterns represent a valid floating point number, because there are bit patterns in the floating point representation which are not floating point numbers, which are NaNs and infinity and all these things, right? And since the compiler is using the bit pattern essentially as the template argument, you would run into the risks that you suddenly generate a template which doesn't represent any floating point number. And what should you do then? And that's why using floating point numbers is not allowed to be, or floating point numbers can't be used as template arguments. But nowadays, the language has a feature which is called const.expr, constant expressions, which essentially gives you the full language, the full C++ language as compile time. So you can do really full computations at compile time and blow up the compiler as much as you want. But we will talk about const.expr another day. For now, just remember, you can do numeric computations at compile time, and that's very interesting and sometimes very powerful. And we will use that feature, or part of that feature, in certain contexts. Okay, that's one. The other thing, what you want to do and what you can do with templates and template meta functions is to do type computations. So instead of returning a value from the meta function, you return a new type from the meta function. And you might say, okay, why do I need that? What is that for? That is not very helpful. Very wrong. It's very helpful, and I want to give you some examples. Okay, let me comment out that factorial. Type computations. A very simple type computation is if you have a certain type, be it integer, double, or whatever, and you want to have a type which is a pointer to that original type. So instead of having a double, you want to get a double pointer. And instead of an integer, you want to get a pointer to an integer. And instead of a string, you want to get a pointer to a string. And you want to do that transformation at compile time. Sometimes that's very useful. We might see examples for that at some point. And especially when you look at, and remember, all of what I'm trying to convey here is to allow you to look at the HPX source code and better understand what we do there. Why do we do certain things in certain ways? Because it might be very opaque from just looking at the source code what is going on. And we do a lot of these type computations because you want to remove a const from a type, or you want to add a pointer to a type, or you want to do certain things in order to adapt to arguments which the user supplies to a generic function. HPX is very much about generic functions. It's about, well, async, right? It's one function which you can use with arbitrary types and with arbitrary arguments, and it will work. And in order to make that work, a lot of type computations are necessary under the hood to do the right thing, depending on what type the user supplies. Okay, so let's write a very simple meta function which we call addPointer. addPointer. So it's a meta function we want to use to take an arbitrary type t and to generate a type t star. And again, we create a meta function. We know how to pass an argument. In this case, it's a arbitrary type t, but we don't know how to return the value from that meta function, or how to return the result from that meta function. And here's another convention, and that other convention says that whatever embedded type def which is inside that meta function, which is named type, is treated as a result value of the invocation of that meta function. And as you can see, when I get a type t, then the result of the addPointer is really just a t star, obviously. Very simple. Or t star star if you want to add 2 pointers or things like that. So let's see how we can use that. Last time I was using that type ID thing just to see what types we have. So let's use that again. Type addPointer int type, right? So I'm using this, my addPointer meta function, invoke it with int, and then I refer to the embedded type of that meta function, which is a result as we agreed on. So the whole construct, what type will that be? If you look at the int star, right? Add pointer to int, colon, colon type, int type def, int star type. So the embedded type alias, which is called type, represents int star. So the whole construct will refer to an int star, which is what we wanted to achieve. So let's try whether that is really the case. Let me add a new line here. And let's print it. And I'm very sorry that it's so small. I can't really increase the font size, but you might discern it, that it really printed int star. So let's, for the sake of it, just add 2 pointers to it. So we use the result, what we got back from the first invocation, as a template argument to another invocation of add_pointer. And we refer to that type again. And guess what? The result will be int star star. See? You can see it. So it's really int star star. So it's a very simple meta function which allows us to generate a new type, which is the pointer to the given type. And we can use that construct to instantiate a new variable. So what I could do is to really do this, the following. Foo equals 0. So I can create a new variable of that type, and that variable foo will be a pointer to an integer. So I can reuse whatever I'm computing using that meta function and use that as if it was any other arbitrary construct which represents a type. Which is very powerful because it allows us to start looking into particular types and do certain operations on them. Let's do another example. Yes?
Let's see 2 examples. One is to return the value. They use both some conventions. One is the value, name of value. Another is the type. In both examples, we have one parameter to this template.
Yeah.
What about if you have multiple arguments? Then in that case, what kind of name convention would be?
Well, if you have several arguments, you can certainly add more template arguments to it, like in a normal function. But like a normal function always returns one value, a meta function will always return one result. And it will be, by convention, be called type or value, depending on whether you want to return a numeric value or another type.
Can you see such example?
Sure. What can we do here? Let's create another meta function, which gives us a, what can it do? Standard map. Standard map is a container which maps a key to a value. And we want to generate a map of particular key values as a result of a meta function. So we need a type for the key and we need a type for the value. So let's do that. Template, type name key, type name value, struct, and let's call it make map and the embedded type def is a standard map key value. So you have one result which depends on 2 different template arguments. Or you could do a numeric computation by adding 2 values, right? So one argument is one term and the other argument is the other term, but the result is still the addition of the two arguments you're providing. So you will always have one thing to return from the function, but you might have several template arguments which represent the input to that function.
In this case, I want to extend it a little bit. It's no longer a mapping, but I want to add a third argument at the switch. If the third argument is 0, we return the type of the first the key, for example.
Yes.
Otherwise, we return the value.
You're very close to that, and we will get there in a second. Give me, and by the way, I already gave you the technique to use for that. It's called template. It's called template specialization, right? If the third argument is a 1, you want to get the first one, and if the third argument is a 0, I want to get the other one. And we can create that easily now because we already have the means to do so. And let's actually do that before we go ahead with our type computations. T1 bool flag Okay, so we have a if, and we want if to return T1 when flag is true, and we want it to return T2 when flag is false. Okay, that's what you wanted, right? So you can write it yourself, it's easy, right? Okay, let's assume we have the base case that flag is true, then we return T1 template. Let's have these two template arguments here. Struct if and now we have to create a specialization for the if template, which is selected when the first argument is false. So very simple, we just say false, T1, T2. So we have a main template which is being used whenever flag is not false, and we have a template which is being used whenever flag is false. And as I said, it's specialized, and even in that case partially specialized. I don't specialize all of the template arguments, but I specialize only the first of the template arguments and leave the others as free template. Others can be arbitrary. Okay? So specialization not only means that I fully specialize a new template like we did in the factorial example where I said, okay, 1, use this one. But I can partially specialize things. I can say, okay, I don't care what these two arguments are, but if the first one is false, please use this specialization. Again, it's kind of pattern matching. It tries to map the template arguments with whatever the specializations are and selects the one which is most appropriate for the context. And that if will give us, oh, well, I have a typo here. I apologize. If it's true, it will give us T1, and if it's false, it will give us T2. Everybody with me? Is that what you were looking for? And that's why I said they are Turing complete, right? We have an if statement. Now we can have a meta function which gives us two different results depending on a flag. And by the way, this gives us almost all what we need for our initial example where we talked about advance and the switching of and the selection of the two implementations of advance. If it's a random access iterator, use this implementation. And if it's not a random access iterator, use this implementation. And now all what's left is we have to figure out whether something is a random access iterator, right? Because then we can just return two types and use these two types to select between the two arguments of the advance. And we will use that, do that a bit later on. Essentially, we will build, or we can use that if I created here to implement that selection. You're not looking too happy. But it makes sense, right? As I said, templates have never been invented to do this. Never. And the syntax of templates is just awful to do these kind of things. Because you don't want to write code in that with these angle brackets and add pointer, something, colon type, add pointer, and so on and so on. But you still can do it, and that sometimes you want to do that because it's the only choice you have in order to generate appropriate and optimal code underneath in your library, or to do selections, which of the algorithms to use, and so on and so on.
Here, I don't understand why we don't need to define one bit a true. And
Well, we could have done that. What we could have done is this. And not provided a implementation of the main template. That would have worked in the same way. But since Boolean has only two values anyway, we just said, okay, if it's false, use that, and all other cases use that one. So it's if you have more than one selection, you might want to explicitly write out everything, but you don't have to do that in that case because, well, essentially you get the same code, right? There's no advantage of, and since it's a Boolean, you can't provide anything else but true or false to that first argument anyway. So what's the difference, right?
I mean, yeah.
Do you agree?
Can I ask a stupid question?
Yes, please.
What happens if you mix up the order of T1 and T2? How does it? So you define it in the template, the line define the template T1, T2,
Huh?
and then in struct you define it T2, T1, just in the opposite order.
Well, those are just names.
Okay.
If you write T2 and T1 and turn that around here, nothing happens because those are just names.
Okay. So
The positioning is the interesting part. So it's doing positional matching between the specializations, not name matching. Okay? Any questions to that? Do you want to see an example how to use that? Might be good. Okay, let's do that. Okay, so we had add pointer. Let's use our if true int double and the same but was false. Okay, so I have one. The first expression is if true int double int, and the second one is false int double. So the first one, what will it print? What is T1? Int. And the second one, what will it print? Double. Well, let's see. Yeah, int double. So for those who can't see it, it really printed int double. So what we invented is a mechanism to select between two alternatives based on a condition at compile time. Okay? Which is very powerful. As we can see, or as we, and this we can use directly for our advanced example. I haven't completed in the very first seminar, and I will get back to that once we have all the facilities we need for that in place. We will write advanced the way we wanted to have that, namely select one algorithm when it is a random access iterator and select the other algorithms when it's not a random access iterator. Yes?
All these things that you're talking about done at compile time,
Yes.
is it similar to what, like those pre-processing statements in the code are also
No, it's evaluating things at compile time.
valid?
It's evaluating things. It's calculating the things at compile time. It does a number computation or the type manipulations at compile time while it compiles things. And then you can use the result of that manipulation in your code and get and just do something with it. Okay? No?
I have a question.
Yes?
Shortly. Okay, in the part that you wrote, strike if false T1, T2, why did you mention both T1 and T2 on that part?
Why did I mention T1 and T2 in this part? The answer is our main template requires 3 template arguments. And I still need to match those. I still need to give the compiler the idea what to use as the second and third template argument while instantiating that type. But in that case, I just leave it open. I say I don't care which of the types are used, any type will do. It's just a syntax you have to use to do the partial specialization.
So here in this example, you just clarify in the cout that what the T1 is integer and T2 is double, right?
Right. Well, we just wrote if, true, int, double. So we provide the 2 arguments, which the compiler will use and plug into that template. So it will use true, int, double, and we'll do the same thing here. But here it will not match because the first argument is not true, it's false, so this template will not be considered. So it
That's why I suppose it should be a strict if for just 2, T2. I don't really
you're right, but
T1 again.
because the template has 3 type arguments.
But the T1 should be appear when it's true, right? And we mentioned it in the first part.
Right. But this is how the syntax is defined. Okay? And as I said, it has never been designed to do these kind of things, so it might seem a bit awkward or strange or not how you would do it. It's just that the template language capabilities are abused to do these kind of things. Okay? The message you can take away is when you do template specialization, you have to provide all template arguments again when you specialize a template. It's not, you can't just specialize 2 of them and leave off the third one. That doesn't work. You have to specify all of them. And it's kind of a pattern matching. So it looks at, okay, what do I have? Which of the template specialization matches best? And that one is selected for that set of arguments. Does it answer your question? Yes? No?
Previously, I was thinking about if both types are used in the body, and how are we going to give the names and reference one with another? But I think that's commonly required in such a scenario where we can use the specialization just return one of the types.
Yes. Well, you can think of meta functions being the compile time equivalent to a normal function which you run at runtime, which you execute at runtime. And the normal function takes arbitrary number of arguments and returns one value. And the meta function takes arbitrary number of arguments and returns one thing, which in that case is a type. And so you can do a one-on-one matching. So function invocation at runtime corresponds to template instantiation at compile time. An if statement at runtime corresponds to a template specialization at compile time and selecting the alternative at compile time based on some criteria and so on and so on. People have built whole languages on top of that. So for loops and you can do, well, as you can imagine, once you have an if statement, you can build a for loop, right, easily. You just count down your variable, and if it's 0, you just stop and you use. But you need an if for that. So the if is a critical part here. Okay. So let's do another. It gets crowded here. Safura told me not to delete anything. So blame her. Okay, we had add pointer. What about remove pointer? If you want to turn have a meta function which takes an arbitrary type, and if it's a pointer, it gives us the base type of that pointer. And if it's not a pointer, it doesn't do anything. Sometimes very useful because you get a pointer, but you actually are not interested in the pointer itself, but you're interested in the type the pointer is pointing to. You want to do something with the type the pointer is pointing to. So you have to remove that star from the expression. How do you do that? Well, you should be able to do that by now. Anybody? Any takers? No? It's not that difficult. Struct remove pointer. And since we have a decision to make, namely, if it's a pointer, do this. If it's not a pointer, do that. We obviously need a specialized template. So the main template, let's use a main template for the case that it's not a pointer. Then, as I said, nothing should happen. Remove pointer should return the type itself if it's not a pointer. But if it's a pointer, we need to specialize that and say, okay, if it's a pointer, hold on, something's wrong. If it's a pointer, well, then return a base type. So as you can see, that specialization is very powerful because it not only allows to match concrete types, but it even allows to match partial types. And this template will be, this specialization will be used whenever I instantiate the whole thing with a pointer. And then I just snip off the pointer part and return the base type from it. Does it make sense?
But what if you
Hmm?
have a pointer to pointer?
Let's try it. Let's try it out. What would you say? Okay, let's use our remove pointer meta function with a pointer. And you're asking what would happen, right? Okay.
You can do it recursively.
If you want to do
Is that recursive by itself or not?
well, we haven't done anything recursive there.
You have the else condition. You will always go up to the default implementation. Then you don't have any more pointers.
Well, let's think again what we have done. Int star. Right? That's what you're asking. What is the result of remove pointer in star? What will happen? Let's just pretend you're the compiler. You're shown this piece of code, and you're having, and well, let me just scroll that in. That might actually be possible. By yeah. So this is the code, remove pointer, and this is those are our two specializations. So when I do that with int star, what happens? What will the compiler do? It will
Second one finished.
look at the specialized one and say, okay, this matches. What is T in that case?
T star.
Int star. So it will use that. So the result is int star. So let's print it. Let's see. Int star, right? So there is no automatic recursion going on there. If you want to apply it recursively, you have to do that yourself in the very same way as we have done that with factorial. You just apply that until you reach the end. Okay? Want to try implementing recursive remove pointer? I mean, those examples you are giving me are very, very nice because they go way beyond what I wanted to do, but they are more practical because they help you understand things. Remove recursive remove pointer. Recursive remove pointer. Okay, how do you implement this? Yes?
Just instead of T, have another call to recursive remove.
Right, instead of T, I just put another recursive remove pointer of T here, and I get what I want. I'll say a word about the type name in a second. So what I do, as long as it's pointer, I reapply recursive remove pointer, and when it's not a pointer anymore, it will use that one as a break condition, as the end condition, and will give you the basic type. That type name is necessary from language standpoint because under certain circumstances a compiler can't know whether the thing you're referring to is a type or a value without analyzing the whole universe. And that's why the programmer is required to specify whether something is a type, then you have to precede it with type name, or whether something is a value, then you don't have to precede it with anything. And you have to use type name inside templates whenever you refer to embedded types in somewhere else. So that is really a purely language thing we have to do. And compilers nowadays are good enough, they will tell you, hey, you forgot a type name there. Something is off, I don't know what to do. You probably forgot a type name, so you don't have to remember that. Okay, so what will our code print now? Hopefully. Let's do 2 more stars here. Int. Okay? So we converted an int star 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 into an int by recursively reapplying the template onto itself until all the pointers have been removed and I have really the basic type I wanted to get. And so on. So you can do very nice type transformations just by doing pattern matching, by saying, okay, I have this, and if I have this, I want to do this, and if I have something else, I want to do something else. And template specialization is the key to that. By utilizing the capability of the compiler to do pattern matching in a very sophisticated way. So you can do partial matching of a type, like here, T star. You can use partial specialization by specializing only one of the template arguments and leaving the others open, or specialize 2 of them and leave the rest free. Or you specialize the whole damn thing, like in a factorial example, where you just say, okay, if it's 1, use this one. And for all other cases, use the others. Okay? Any questions so far? No? Yes?
Regarding the keyword, in most cases, the keyword type name is interchangeable with the class. But for the template class, it's preferable to using class.
You mean type name? Okay. The keyword type name in the template declaration is okay. You can use either type name here or the keyword class to say this is a template type argument. So you can write class T or type name T. It's a pure conventional thing. Everybody does it differently. I just decided a couple of years ago to use type name there, always. But you could have written, I could have written class here. This is completely interchangeable and no semantic difference whatsoever. But this type name used here has nothing to do with this type name. It's just the same keyword used for 2 different things. In one case you say this is a type template argument, and in the other case you say the embedded type I'm referring to, the embedded thing I'm referring to is actually a type and not a value.
So in body, we have to use type name, right?
You have to use, here you have to use type name, you can't use class.
Is there any scenarios that we have to use class other than type name?
No. No. This is interchangeable, you can use both. It doesn't matter which one you use. I personally use type name. HPX and Boost uses type name most of the time. So it's really conventional. Some people do it that way, some people do it that way. Standard libraries of all compilers I know usually use class there. So if you look into a standard header file, we probably will see that it's using class there. So let's see. Yeah, that's the definition of my vector. They use class as a keyword there. So it really depends who is doing that.
Do you know why there is 2?
Ask the forefathers. I don't know. You know, some of the things in the language just stem back to either oversights in the definition, which then got into people's code, and nobody wanted to go back and break half of the existing code base. Half the things, many things have an actual reason to it. The pity is that nobody remembers that reason, so I can't really explain to why that is the case. It's even that way. I don't know if you have heard about the books from Myers. What's his first name? Scott Myers. Effective C++, effective STL. He has written, I don't know, 5 or 6 books about C++ and how to use C++ effectively. But essentially, these books are all about explaining the quirks of C++ and the idiosyncrasies of C++, and trying to find reasons why C++ is the way it is and what you can do with it, and how you can write code which is easily understandable without going into these quirks and so on and so on. So essentially, this guy made a living, and he retired recently. He made a living out of those idiosyncrasies of the language. He has written nice books, and they are very nice. So when you want to know really deep, get a deep understanding of certain things in C++, Scott Myers' books are definitely the go-to, and almost a must for everybody to read when you want to do real massive C++ programming. But this guy just made a living of it. So you can make a living of idiosyncrasies, of oversights, and I talked to him once, and I said, hey, do you really can explain all these nitpicks and idiosyncrasies in the language? He said, nah, I can't. And trust me, I have talked to everybody I could talk to. So nobody remembered why certain things are a certain way. So, well, it's the way it is. It's a language which has grown for 40 years now and has so many warts and barnacles and whatnot. So it's very difficult to explain every nitpick. That's why it's so important that you just choose and decide on certain conventions for yourself, which language features to use, which language features not to use. I decided for myself that I'm not going to use pointers and arrays, for instance, because I think that is just, you shouldn't use ever. Well, we talked about that right in class for extensively, and other things. Or if you want to do something, use this way of applying the language to it. If you want to write a meta function, use type as a return, as a name of the thing it returns, and so on and so on. So it's a lot of conventions which people kind of got used to, and which makes the code usable and maintainable and understandable for others. Marcin.
It's one of the conventions I noticed, which SPX chose to use always typedef instead of using.
Yes.
And I would like to ask, is it possible to typedef a template? I know it's possible with using, to define a template using something.
Okay, so the question is, just to repeat that for the camera, HPX uses typedef to define a type alias for something else. Typedef essentially gives this construct a new name, right? That's all it does. Newer language capabilities, C++11, have introduced a more powerful way to define type aliasing. The reason why HPX uses typedefs is purely because we support compilers who don't know anything about the new way of doing things. That's why. And once we get rid of GCC 4.6 and 4.7, we can switch to the new way of doing things. The other question, can I use typedef to define a template alias? You can't, and that's the problem. And that's one of the reasons why they introduce the new syntax and the new mechanisms to do aliasing, which is much more powerful than the typedef one.
Yeah, the only way I could find is just to have a template with structure inside of this.
Right, here, derivation.
Yeah.
It's the only way to do things. But you don't need that too often. Yeah, okay. Okay, so add pointer, remove pointer. We talked about meta functions. So essentially what we introduced is a way to define meta functions using templates, which can be used for two things. A, they can be used for numeric computations, as we did for factorial, and you can use them for all kind of type manipulations. And for both, we have a convention, namely the numeric values are returned through a variable named value, and the type is returned through a type alias, which is called type. What I want to do now is to introduce two very simple facilities which are so useful that they ended up in the standard by now. Namely, a facility, a type which represents a Boolean value true, and a facility which represents a Boolean value false. And I'm pretty sure you should be able to write that yourself. Struct true type static bool const value equals true. And the other one is we call false value. And this one has embedded, sorry, they are not templates. What am I thinking? They are not even templates. Two types which allow me to represent a numeric value, true and false, in the type system as true value, true type, and false type. And since we want those to be true meta functions, we not only give it a value, but we also give them a type. But for simplicity, and since for lack of an alternative, we just let them return their own type as their embedded type. So we have two meta functions which we can use for numeric computations, and we can use them for type computations. But they are very simple in terms of type computations because they just return itself whenever used in computations. And you might say, hey, why do we need that? That's complete nonsense. As you will see, this simple trick to let the meta function return its own type as a result is very, very useful, and we can utilize it everywhere. And we will see a couple of examples. Those types are in the standard, and they are called true type and false type. So there's std : true type and std : false type. They are so useful that people decided to implement them in the standard. And the next thing is to use these type for something useful. And we already talked about meta functions which can transform a type, like add pointer and remove pointer. But you can have also meta functions which give you information about a type. For instance, is void. Is this thing I'm giving you, is that void? Or is that an integer? Or is that an integral type? Or is that a random access iterator? Or is that a pointer? Or is that a reference? Or is that thing const? Or is that thing non-const? Or whatever. So we have, and those things are all in the standard nowadays, we have several classes of these meta functions. One type of meta functions which allow us to do type transformations, add pointer, remove const, add reference, all these things. And another class which is kind of type introspection, traits, and those things are called traits. They introspect a given type. They give you information about a type. What is that type? Is that an integer? Is that a random access iterator? Is that a pointer? Is that a reference? Is that const? And so on and so on. And what I want to show you is how these type traits are written. And the interesting thing is that these type traits always return either true type or false type. So these are really the basic return values used for these traits. When I do is void, then is void evaluates either to true type if that thing I'm using it is void, or it evaluates to false type if that thing is not void. So let's do that. Let's write isPointer. Let's check whether a given thing is a pointer or not. Type def template. Template type name t. Struct isPointer. And let me quickly copy that. Where are we? Here are we. So we have to make a decision. As before, we have to do one thing if the thing I'm getting is a pointer, and another thing if it's not a pointer. So we do pattern matching again, right? Oh no, I just put it in the wrong spot. Sorry. The main template always has to come first. You can't specify the specialization before the main template. That doesn't work. So this is our main template, which will be used if t is not a pointer. And this is the specialization which will be used when t is a pointer. And all what we have to do now is to say, okay, if it's a pointer or if it's not a pointer, we derive that thing from false type. And if it's a pointer, we derive that thing from true type. Right? And that automatically gives us the value, the value of these two meta functions, true and false, if we want to use it for numeric computations or for numeric analysis. And it gives us the embedded type alias called type, which represents the thing, the compile time equivalent of true and false, namely true and false type. So essentially this can be used or will be used wherever a true type is expected. And this can be used to select something which is false type. And now we are getting very close to that implementation I was talking about the advanced algorithm.
Are those braces necessary? Are those braces necessary?
Yes.
Okay.
Well, it's normal derivation. You create a new type and you derive it from two type.
No, but the braces.
Oh, sure, well. Okay, because nothing is in there, right? So it's empty types. But since it is derived from true type, the things true type contains are contained here implicitly. So isPointer has an embedded value and an embedded type, which represents true type. So this is a full-blown meta function as we have it, as we talked about. It has both things because it derives, it inherits these things from its base class. Okay, and this thing can give us the information whether something is a pointer. So let's try that out again. isPointer star star star. What will it print?
Yes, sure.
It will not print yes. It will probably print 1 or something. Struct true type. Okay, it gave us a type of the thing. And so you already can see that even if I used isPointer here, but the result is still true type. So the type that thing evaluates to is true type. And what I could do here instead is just use the embedded value. And that will probably print true, or 1 or something. Yes, 1. It printed 1. And that shows you that this is a true meta function because it has both. It has the embedded type, which is true type, because it is the type def inside the true type we define to let it refer to itself. And that's why it's so useful to do that. Or we could use a value which is defined inside true type as well, which is true, which is essentially 1. Okay? So there's a whole class of type traits which all start with is underscore something, which you can use to do type introspection, which give you the standard true type or standard false type equivalent from the standard, depending on whether the argument to that type trait is fulfilling the criteria that type trait is defining or not. Any questions? No? Well, it's not that difficult in the end. It's really fairly straightforward. And it's all about conventions. So people start building these conventions around these basic facilities. And when you, in somewhere in the code, you see a template is pointer something colon type, then you don't start digging what that is pointer is doing and how that is being done, because these type traits can be very complex sometimes to do these type analysis. But you really understand immediately, okay, that just gives me true type or false types depending on whether that thing is a pointer or not. So you're building these higher level abstractions without even understanding what the template actually is doing. And most of the time you don't even want to understand how these type introspection templates are being written, because they are fairly tricky. And in the early days, by the way, when Boost was invented, and Boost has invented all these type traits, the compilers were weak and old and not standards conforming. So some of the implementations of those type traits were using compiler bugs, because they knew this particular compiler, if I write it that way, will do exactly what I want, because there was no other way to do it. So you had broken C++ code, which is in Boost, still in Boost. You can look at that. It's completely broken with a standards conforming compiler. It wouldn't even compile. But that particular compiler, and the Microsoft compiler, is particularly bad in that would interpret that code wrongly, but would do the right thing so that you could use it to analyze, to do type introspection and things like that. So that was kind of very interesting. Well, 10, 15 years ago, I'd say. But nowadays, these things are all standardized and very clearly defined what they do. And you have it in the standard library at your disposal. And we use these things in HPX quite extensively. So if you look through the source code, you will find a lot of those is underscore some things. And even further, we have defined a whole set of these type traits on our own, which represent the type classes of which are used in HPX. Is executor, is execution policy, many things, which we have defined in HPX ourselves in order to allow us to do these introspections for our needs. Okay. And the last thing I want to say before I shut up today. I have still a nice one point on my list here, but we will not talk about that today. It's too much to talk in 10 minutes, which is Sphene. Have you heard about Sphene?
Well, something failure is not an error.
Yeah, let me do that. Computer? Chris, what do I have to press?
Computer, yes.
Substitution failure is
Yeah, it's not an error.
Substitution failure is not an error. We will talk about that next time, which is another language feature which is essential for the language itself. The language couldn't live without that, but people are notoriously, how can I put that? Abusing, or there are probably better words. I'm looking at Adrian, he might have a better word. Obnoxious. It's probably a good word for that. And people go to abuse that language feature to do something, to control it. And that is something you have to understand when you look at HPX code, because that is used everywhere. But we will talk about that next time, because I will not be able to cover that in 10 minutes. But which one is that?
Maybe display or display port.
Display. Yeah, okay. But what I want to mention here is one particular thing which we learned to use and learn to utilize very widely. One of the advantages of C++, since it has templates, is a feature which is, I don't even know how to describe that properly. Normally, when you write a library in Fortran or in C or in other languages, those libraries have well-defined APIs. They have a function which is exported, and you can call that function, and that library will do things for you, like MPI send. It's a function which is well-defined. You can Google it. You find the specification. It has 3 or 4 parameters, and you have to specify these types, and it will do whatever you want. And this is the way how almost all libraries in C and Fortran and other languages are written. When you look at C++, you certainly can write libraries in the very same way. You write a function which has concrete types, you use it, fine and dandy. But what C++ allows you to do is to not have a strict defined function API between your application and the library, but it allows you to write a code which has a very fuzzy boundary between the application and the library. Kind of the application reaching into the library and the library reaching out of the library into the application. Which is especially useful when you want to use application-specific types, which only the application knows about, and still influence what the library is doing with it. One example would be you want to write a very efficient copy algorithm, which copies things from A to B. But you know that certain types can be copied more efficiently than other types. If you have just a byte stream, then all you need to do is to copy these bytes bitwise over to the destination. And you can do that with memcopy. Memcopy is still the most efficient way to copy things because it's optimized for the underlying architecture and is doing bit stream copying very, very efficiently, as efficient as it gets. But other types like things which have a constructor or which have references to external things and you have to do deep copying of those objects, you can't memcopy them, but you have to copy each element separately. You have to have a for loop and take one and copy it over and copy it over. So you have different implementations for different types that copy algorithm is used for. Now that's fine, but sometimes the library doesn't know anything about a particular type which is used in your application, which doesn't look like being bit copyable, but the user knows, or the writer knows, hey, that thing is bit copyable. It doesn't look like it, but it's safe to memcopy that thing over here. It still has constructors and destructors, but no harm happens when I memcopy that over. So you want to reach into the copy algorithm and tell the copy algorithm, you know how to distinguish these things, and you know how to decide whether to optimally copy or to do the slow copy, but you don't know anything about this type. I have. So I'm going to tell you that it's safe to apply the optimization for this type I'm giving you. So you're reaching from the application into the copy algorithm, which was written by other people 15 years ago, and you still tell it to use the optimal one for that particular, I don't know, food type I created. So you're blurring the boundary between the library and the application in a very, very powerful way, because you can reach into the library and can say, hey, I know it's safe, do this. And for the other case, oh, okay, you decide what to do. So you can use templates and type introspection mechanisms to guide the library to do optimizations on its own, but you can use these type traits also to supply the library with knowledge about your types. So now let's assume that the library makes that decision whether it can copy something efficiently or not based on a type trait which is called I don't know, is trivially copyable. Okay? And that type trait is in the library, and the copy just uses is trivially copyable on the type it receives, and then it makes a decision whether to do the optimal implementation or not. But that is trivially copyable default implementation doesn't cover my particular food type. So what do? I write my food type, and I provide a specialization for the is trivially copyable type trait in my code, which does return true. And then the whole thing is compiled together, and the library will use my specialization of the type trait together with the default implementation of the type traits, and will still make the right decision and will use the optimal algorithm for my food type. And I will show you an example how that actually works. We call these things in HPX customization points, because they are special templates which are well defined, well documented, and the user is allowed to provide specialization for those templates in his own code, and the library will pick up that specialization and will guide the library to do things differently based on what the user provides and information to the library itself. And that's what I mean by reaching into each other, right? So the application decides what to do, what the library will do, and the library reaches out into the application code and grabs stuff from there to decide or to get additional information about the things that the application passes on to the library. And that allows you to build these kind of, people call them active libraries. It's not a strict interface between the two, but it's a very fuzzy, blurry line between application code and the library code, because these two are intertwined using the template specialization mechanism. That also tells you that you can specialize a template after the fact. The library provides you a certain customization point with a default implementation of is trivially copyable, and the application, which was written 5 years later, provides a specialization for is trivially copyable for a particular type the library has never heard about, and then you compile the whole thing and it will still work and do the proper thing. So that is the real power of these specializations combined with type introspection, because you can write library in terms of type introspection without saying, okay, if it's int, do that, if it's double, do that. But you write the library in terms of is trivially copyable. If that gives you true, you do the optimal thing, and if not, you do the default thing. And you document those customization points to the user so that the user can provide his own specialization for that template for the types which are used in the application, and still customize the behavior of the underlying library. This is something which is very, very specific to C++, and you don't see that anywhere. That's why it's kind of unusual. And in addition to that, all of that happens at compile time. So when the compiler is done, all that magic goes away, and you end up with optimal code for the types you've been using and you pass to your library. This gives you that is where the real power of those templates lie. Not in being able to do a coordinate with floats and doubles. Hey, okay, that's child's play. But where you can write libraries which expose concepts, which expose facilities and not functionality. And that is where the real power of all of that comes from. Customization points is something which relies on conventions as well. You will see customization points essentially in two libraries. If you look around, well, other people might do it nowadays as well, but I know of two libraries who do that. One is Boost Spirit. It's a parser library, which was written by Joel de Guzman. He sits in Manila. And myself, we invented that 15 years ago or so, that technique. And now we use it very heavily in HPX. Other people might do it differently, but I still believe this is one of those things which really give you all the knobs and handles you need to write libraries in a proper way. I'm telling you that not to brag or so. I'm just telling you to help you to understand what is going on when you look at HPX code. because if you look at the inners of HPX, you will be lost if you don't understand the patterns which are being applied there. But if you know what are the patterns and how our things are being built and what principles are being used and what conventions are being used, then you can read that code like any other code because, oh, okay, it's just an is pointer with a type, okay, done. But you will understand, okay, this is in a traits namespace, so this is something the user is supposed to overload if needed and gets different behavior and so on. Marcin is currently doing that, playing that game with the GPU stuff where you optimize that copy algorithm. What he's doing, when you work with GPUs, you have to copy data over to the GPU and you have to copy it back. But we want to use a standard copy algorithm for that, the parallelized copy algorithm from the STL. So what we have is a customization point which tells the copy algorithm how to copy data. And for the GPU, the copy is being done using CUDA. And when you are copying between memory of the same node, you just use memcopy. And if you copy over the wire onto another node, it uses HPX functionality to copy data over. But all of that behind the same standard or parallel copy from A to B. So the user uses the same API, but underneath completely different things happen depending on the context, depending on the data you provided. So if the destination is on a GPU, things will copy there. If destination is on another node, things go there, and so on and so on. So very nice because it allows you to build higher level uniform interfaces and let the library decide to do the right thing depending on the types you provide to the library. Okay, any questions? I will talk about that a bit more detail, kind of hand wavy for 10 minutes just to give you a sense, but we'll dig into that more detail later on. You have a question? No? Good. Safura is happy, so we can just wrap up. Thank you so much.